Hello everyone, this is Shishir and you are watching GATE Academy Global, and in today's MOSTOK session, which is lecture number 4, we are going to analyze the MOSFET in terms of its operation. Because in the previous session, we have analyzed the MOSFET in terms of its structure. I have given you two types of structure, that is 2-dimension and 3-dimension. And in 3-dimension, we have done some numerical problems also, two numericals. Based on that one, we come to know that where the junction is actually present inside the MOSFET. Okay, so in today's session we are going to analyze the operation of the MOSFET beyond the structure of MOSFET, and we are going to understand what is present inside the semiconductor body and how this particular semiconductor is behaving when we apply different potential at the gate terminal and the drain terminal. So student, I think you are aware of this particular fact that in an enhancement type n-channel MOSFET, we are applying only two potentials, and those two potentials are applied at the gate terminal and the drain terminal. And if you think that we have 4 terminals, yes, you are right that we have 4 terminals, but among these 4 terminals, only 2 terminals are used for applying the voltage. The other 2 terminals are get short circuited and they are grounded. So I want to classify what are the steps that has to be used when we trying to understand the operation of MOSFET. In addition to this one, we are going to solve some questions that is based on MSQ and quizzes that is based on the theoretical aspects of the semiconductor devices. And we are going to analyze the whole things today in today's class to understand the behavior of MOSFET, because the students, if you visualize perfectly the semiconductor behavior due to excitation, and the excitation that is applied here is nothing but the voltage, and if you understand how separately we can handle these two voltage, that is gate terminal voltage and drain terminal voltage separately, to understand what is happening inside the semiconductor, then definitely you can be able to answer so many questions in gates that based on these particular facts, that what is the behavior of the semiconductor due to application of different voltage values at the gate terminal and the drain terminal. So students, I am starting from the first point, that is the first thing that we have to understand is, you don't confuse yourself, because I am going to analyze an enhancement type MOSFET. I just write here, this is in enhancement type MOSFET, and I have given you the classification of MOSFET in the second lecture of MOSTOK, and in that we have seen that what is the difference between enhancement type MOSFET and the depletion type MOSFET. So basically I am using here enhancement type MOSFET, and that too an NMOS, that is we have to create a channel of electrons. Since it is, this MOSFET is having only one type of charge carriers, that is unipolar, that is only one type of charge carrier is responsible for the current conduction, that's why it is called NMOS and PMOS. So I just want to name here the first one that we are going to see inside the operation. This is the operation of MOSFET, and I want to create a channel. This is the first thing that you have to understand inside the MOSFET. And the second thing, that you have to create a channel. After creating the channel, we want the current. But for getting the current, we have to, for creating the channel where we have to apply the potential, we just need to apply the potential at the gate terminal with respect to source terminal. And we know that for creating the channel, which is a conductive path between source and drain, we have to apply a potential which must be greater than the threshold voltage. And students, I already given you the analysis about what is this gate terminal voltage, what is the threshold voltage, and why we can only be able to create the channel when we apply the voltage that is greater than the threshold voltage. There is a constant voltage value above which if you apply the gate terminal voltage, then only you can see the inversion layer, that is the channel has been created on the semiconductor side. Okay, then we have to apply a potentials. Then we have to apply a potential where one is gate terminal, second is the drain terminal. So apply a small voltage. We need to analyze after applying a small voltage value at the drain terminal, and that voltage value is nothing but the voltage applied at the VDS value. And a small voltage, that means I will take that the voltage is approximately, I will say that is 50 millivolt, or we can say less than 50 millivolt. Okay, I just mean to write in this way. So I will not going beyond this 50 millivolt, and I want to get an analysis. This is the typical value, not the exact value. So for any type of MOSFET, for any one type of model of MOSFET, we are applying this particular voltage. Okay, typical value. Next is the third one is I am increasing the voltage value. I am going to increase the voltage value. Which voltage value? Similarly, VDS value. So increase the voltage, that means the value of VDS above, increase the voltage VDS above, that means 50 millivolt. This is the typical value. That means if we increase the voltage value, how we can understand the behavior of the semiconductor. In addition to this, we are going to see the characteristic, and we want to solve one numerical also. Numerical means MSQ only, and that is nothing but this particular one. Okay, what is the question here? With the potential difference between the source and drain kept small, that is VDS is so small. I have written here, we have applied a potential at the drain to source terminal which is small, that is a small voltage at the drain to source terminal. The MOSFET behaves as a resistance. It is already given that the MOSFET is behaving as a resistance whose value varies inversely with. We have to analyze that what is the value of the resistance that is given by this MOSFET, or that is produced by this MOSFET when we apply a very less potential, that is VDS is very small. And we have to analyze that what is this overdrive voltage, what is this aspect ratio, what is transconductance parameter. Statement is in the question is not suitable. So we cannot find out this one, that is another option. So we have to understand what is the overdrive voltage. This is one terminology, and I will give you the reason of why we are using this terminology and what is the meaning of this terminology, overdrive voltage. And what is the aspect ratio, what is transconductance parameter. These are three different parameters on which I can say the resistance that is offered by your MOSFET will get dependent when we increase the voltage of drain terminal, not the gate terminal voltage, drain terminal voltage, and that voltage is very small. So this is one type of MSQ that we are going to solve here, and you just have to understand these three things under the following topics, that is create a channel first and then apply a small voltage, then increase the voltage VDS above 50 millivolt. So we are going to start this particular analysis from this diagram. I think you are aware of this diagram. This is the diagram of MOSFET, and we have that we have four terminals here. One terminal is the first one, that is body terminal. Then we are having source terminal, gate terminal, and the drain terminal. Here the gate terminal is the controlling terminal which is controlling the conductivity of this path between source and drain. So this is N plus region, this is N plus region, and we are having, this is a P-type substrate. What is this P-type substrate consist of? This is consist of acceptor atoms, and acceptor atoms can be drawn in this way. If you want to know how we can draw the acceptor atoms, the acceptor atom consists of a negative ions with some holes. Negative ion with some holes. That means we are having some of the amount of negative ions with some holes. So we are going to understand the behavior of the semiconductor in today's session. We are going to draw the characteristic. We want to find out the resistance offered by the MOSFET when we apply a very small potential at the drain terminal, in addition to the potential that is initially applied at the gate terminal, which will create a channel. So we are going to start the analysis one by one. So I want to say that we are applying a potential at the gate terminal, and we are going to increase this potential. So if someone asks you what will happen if we are not applying any potential at the gate terminal and drain terminal, how the behavior of this channel, I want to say the behavior of this particular channel which is between this source and drain terminal can be analyzed or can be visualized. So I mean to say that we are going to analyze this part, but if someone asks that what is the behavior when we are not applying any potential, that is this particular terminal is grounded, this is grounded, and this is also grounded, and we can say that this terminal is also grounded. What is the behavior of the channel? I want to say that the behavior of the channel is like that. Since it is P, this is N, we are having a depletion layer between this N plus region and P region. And the width of the depletion region is more towards the P-type substrate, because already we have analyzed in the lecture number, we can say in the second unit. The crash course of the second unit is available in GATE Academy Global, and we understood that whenever we are having PN junction and if we want to find out what is the depletion region present and what is the width of the depletion region present when we never applied any potential at any of the terminals, that is, if the source terminal is grounded, body terminal is grounded, in that condition, the device is in equilibrium. If the device is in equilibrium condition, we definitely have a junction and the width of the junction is more towards the P-type substrate because it is lightly doped. And I want to say one statement, you just remind this statement whenever we are having PN junction, and the statement is about the depletion region, because the depletion region is the active region of a PN junction, and we know that depletion region always present whether we are applying a potential in reverse direction and whether we are not applying a potential, that is in equilibrium condition also we are having a PN junction, and the width of the depletion region is always more towards the lightly doped side. Hence, we are having the depletion region more towards the lightly doped side, that is P side. It doesn't mean that we don't have any depletion region towards N side, but the width of the depletion region towards N side is very less. Very thin depletion region are present in the N side. So similarly, we can say on the other side. On the other side also, we are having a very large depletion region towards P side. And since this is also in equilibrium, the width of the depletion region that we are getting on this side will also be similar to the width of the depletion region on this source side, but we are having a similar depletion region on this particular side, that is N plus region, which is very less compared to the width of the depletion towards the P side. And this particular red line is representing the position of metallurgical junction, where we are separating the N region and P region. And inside this white line representing that there is some depletion region. This is not, this shaded region is only the depletion region. I think you are aware of this particular depletion region. Depletion region is always present at the point where we are connecting both the device. So this is the region. Okay. If I shade, then it will get changed. So this is the shaded region, and in this shaded region we are having depletion region. So I want to give you an analysis that inside the depletion region we are having the ions. On the white side we are having the positive ions. On the white side we are having the positive ions because this is N plus region, and N region consists of the ions which is positive ion with electrons. And if you remove the electrons, then we are having the positive ions that is towards the N side. And if you are talking about the P side, then in P side already we have drawn here. In P side we are having the ions, that ions is nothing but the positive ions, that negative ions, I am sorry, because in P side we are having negative ions with holes. When the holes recombine with the electrons, we are getting the ions. So these two are like this. So these ions which is present on this particular side will have an electric field, and we are having the direction of electric field because I have already drawn the positive ions inside this box, red box, and negative ions outside this box, and the electric field is always directed from the positive to negative. So we are having the electric field which is in this direction from positive to negative. You just keep these things in your mind whenever we are analyzing. So there must exist an electric field. This electric field is exerting some force to the electrons when the electrons come inside the vicinity of this electric field. So you just take this one also in your analysis, that suppose I will place an electron here, and we know that there is no mobile charge carriers present inside this particular electric field area because it is called the depletion region. And if somehow a electron manages to come inside the depletion region, this electron will experience a force in the direction opposite to the direction of electric field. So if you are having an electric field in this direction, suppose we are having an electric field in this direction. So from top to bottom, then definitely, actually this electric field is in this direction. If one electron is present here, okay. So we are having an electric field, okay. Here we are having an electric field, and always the electric field is towards from right side to left side. If the electrons comes inside the vicinity of this electric field, then this electron is experiencing a force. And we know that what is the force experienced by the electric field? The force experienced by the electric field is minus Q into E, where the electrons is experiencing a force opposite to the direction of electric field. If I say the electric field is is from right hand side to left hand side, then we can say the electrons which by chance comes into the vicinity of the electric field, then it will experience a force in the direction opposite to the direction of electric field. So I mean to say that this is the direction of electric field and this is the direction of electric field when it comes inside the channel, and this is the direction of the force. So that means if electron managed to comes within the vicinity of this electric field, this electrons will experience a force. This is the main thing to understand before trying to visualize anything inside the semiconductor body. So I want to take this particular part into my analysis, and I want to change the slide, and I will take another one. Suppose this is next one, and I just copy this one. Okay, I just copy this one and I will place. Okay, I want to copy this one and I want to place this one in this slide. Okay. Okay, so this is another MOSFET, and now we are applying a potential. So the first thing we understood is what is happening when we apply VGS, the gate to source voltage, and this gate to source voltage is less than threshold voltage, suppose, and we are going to add this terminal with ground and this terminal with ground we are not applying, and this terminal will ground. So there are only two potential. Obviously these two terminals, source and body terminal, are always grounded. In an enhancement type, this is source terminal, this is body terminal. We are applying a potential at the gate terminal, and suppose we are not applying the potential up to the required value to create an inversion layer, that is the gate terminal voltage is less than threshold voltage, then there is no inversion layer created. If there is no inversion layer created, then we can say that the potential here is positive, we have applied, and this is negative, and this is with respect to source terminal, and the source terminal is grounded, and we somehow managed to apply a potential. It is VGS less than threshold voltage, VGS less than threshold. What happens inside this semiconductor? If I ask a quiz, then what is present inside the semiconductor? Since it is having a n plus region here and it is having a n plus region, no inversion layer created, and theoretically we know that here we only have the ions. Why we are having the ions? Because we have applied a positive potential at the gate, and this positive potential will create a positive charge in the gate, and we have to take care that the capacitor should be happy, and the capacitor must create a positive charge on the gate or the metal electrode. Then definitely the corresponding negative should be present on the semiconductor. Then we are having a electric field, we are having a capacitor, and that can be seen here. This is when we are applying a potential at the gate terminal which is less than the threshold voltage. And if you apply a potential at the gate terminal which is greater than the threshold voltage, and if you are having a MOS like this, semiconductor, metal oxide semiconductor, then again I can say that we are having a potential that is applied at the body terminal which is at ground potential here, and this is body terminal, this is source terminal, this is gate terminal, this is drain terminal, and this is n plus region, this is n plus region, and we are applying a p-type, having a p-type substrate. Okay, so this source terminal is also grounded here, and the drain terminal is also grounded here, and we want to create a channel. So if you want to create a channel, then this is under which particular classification? We are creating a channel. So this is a create a channel within this particular steps. For understanding the behavior of MOSFET, the first is creating a channel, and we are understanding how to create a channel. So we have applied less than threshold voltage, we just have the ions, Okay, when we apply the potential at the gate terminal which is a positive potential with respect to ground, and we don't have the, we have less create a channel. So just we are applying a potential, this is positive, this is negative. And if you apply a potential that is gate potential which is greater than the threshold voltage, then definitely a layer of electrons has been created on the surface of the semiconductor, and this layer of electrons is known as the inversion layer. So we are having the layer of electrons on the surface of the semiconductor like this, layer of electrons on the surface of the semiconductor. So how we can visualize the surface of the semiconductor? Do we have the ions? If I ask this question, yes, we have the ions also, we have the ions, but this ions will take some space. This is the ions which is present, and these are the electrons. When we draw the three-dimensional view of the surface of the semiconductor only, this region, if it is drawn separately for understanding how the surface of the semiconductor is looking like, we just create a small area. This is the semiconductor which we are taking here, and I have drawn only this part. Which part? I have drawn only this part, this dark part. Okay, just understand this one. So here we want to see where the electrons are present. So we just draw a three-dimensional view like this, and we know this is the width of the channel. Where is the width of the channel? This is the width of the channel. So I just want to write this is nothing but the width of the channel W. This is the width of the channel, and this is the depth of the channel. So we have the depth of the channel. So this is the surface, and I know that we are having another parameter here which is known as the length of the channel, and the length of the channel can be written as L. This is the length of the channel. So just I am writing this is the length of the channel, and I want to give you a separate, this is the length. So here also we can manage to draw the length from this particular point. This is the length of the channel, and it end up to this point. This is the length of the channel, and I have drawn by taking the length of the channel. So the electrons which is present here is present actually on the surface of this particular channel, and the ions which we can see here, it will take definitely some space because these are immobiles, and these ions consist of what? If I ask you, this ion consists of inner electrons and the nucleus, and the electrons are the mobile electrons. So they will present on the surface of the semiconductor. So this is just like a dust particle on the surface of a table. When you reach your classroom in the morning session after a few days, then you can see some dust particles are placed on the surface of the table. So this particular electrons which is present here, this is having a density which is known as surface density, not the volume density. So this is having a density which is known as surface density. So actually, for proper visualization in 2 dimension, we are creating the electrons in this way. And if you increase the gate terminal voltage greater than the threshold voltage, suppose we are applying a gate terminal voltage that is equal to the threshold voltage, and if we increase the gate terminal voltage is equal to threshold voltage plus 0.5 volt, we are increasing. We are having more number of electrons right now here. So the more number of electrons can be drawn like this. So if we increase the gate terminal voltage above and above, we are having on the surface of the semiconductor more and more number of electrons that can be calculated by a particular unit which is known as surface density, and this surface density of electrons can be written by an unit, that unit is coulomb per centimeter cube, not centimeter cube, it is actually centimeter square. So the ions are also present, the electrons are also present. But for visual analysis we are unable to draw this particular diagram again and again. That's why if you are having more number of electrons, we can draw the depth of the channel is increasing like this. So under the condition, if you are not applying any VDS, and we have created a channel, so I will write here, if VGS is greater than threshold voltage, and if you apply more magnitude of gate terminal voltage above the threshold voltage, then we are having more and more number of electrons within this channel, and the conductivity of the channel will increase more and more. Okay. So I want to write here the condition that if you are not applying any voltage at the drain terminal, that must be equal to 0. So we are creating the channel, and the conductivity of the channel will be increased more and more. That means more number of electrons will be present inside this channel. So this will increase the channel conductivity. So whatever voltage we are applying above the gate terminal voltage, suppose we are applying the voltage at the gate terminal which is threshold voltage plus 0.5 volt, then we are applying the gate terminal voltage which is given by threshold voltage plus 1.5 volt, then we mean to say that we are increasing the channel conductivity more and more by getting more number of electrons. So here we are having the ions and electrons both are present. Why ions? Because less than the threshold voltage we have the ions, and these ions are present if you apply the potential greater than the threshold voltage inside the semiconductor also. So the potential that is greater than VGS minus VT, which is called, actually what it is called, this is called the overdrive voltage, the voltage that has been applied at the gate terminal above the threshold voltage. So VGS minus VT is called overdrive voltage, or this is also called the excess voltage. This is also called the excess voltage. So there are many names, but in general we are using overdrive voltage here. So these are the names. I think you understood that what is happening when we not apply any drain terminal voltage, only the gate terminal voltage which is less than or greater than the threshold voltage, in that case we have analyzed. Now we are applying a small voltage at the drain terminal, but already we have applied a gate terminal voltage. So first thing that we have to write here is nothing but we are understanding the second condition. What is the second condition here? Second condition is the condition that we have taken in the initial slide. That is, we are applying the drain terminal voltage, but the drain terminal voltage is small. So we can see from here, the apply a small voltage at the drain terminal, but it is very small, which is approximately equal to 50 millivolt. So we are going to analyze that part. So in that case also, the gate terminal voltage is greater than threshold voltage. That means already the channel is created. So we are created the channel like this, and the electrons concentration at the source end and the drain end is equal. The reason of this equality is the equipotential surface. So if we apply a potential at the gate terminal like this, and the potential is a positive value with respect to grounded, and this is greater than the threshold voltage, just I want to write here, we have applied a potential at the gate terminal, and this is greater than the threshold voltage, and it is a positive potential, which is positive this side, negative this side. And I already told you that this metal is an equipotential surface. All the potential that is present at the source end, at the drain end are equal. There is no change in the positive marks. So in that case, if you are not applying any drain terminal voltage, then in that case the number of charge carriers that is present on the source side and the charge carriers that is present on the drain side are equal. That means the depth of the channel under the condition when the drain terminal voltage is equal to 0, when the drain terminal voltage is equal to 0, the source terminal voltage is equal to 0 and the body terminal voltage is equal to 0, and we just apply a gate terminal voltage which is greater than the threshold voltage, the depth of the channel, this is known as the depth of the channel. So I mean to say that in that condition, I want to write here the depth of channel, because in 2 dimension we are analyzing this condition. What is the surface density? Surface density can be analyzed by using the depth of the channel. So I mean to say that the depth of channel is equal at source and drain sides. So it means only the depth of the channel. So this is the depth of the channel, it is equal on source and drain side both. So this is the thing that we are going to analyze before taking any potential at the drain terminal. So the depth of the channel is equal. That means equal number of electrons are present on source side and drain side. Now when we apply a potential at the drain terminal and that potential is very less. So if VDS we are applying and this is greater than 0, then definitely we are having a current. So we just remove this part, this is not 0, but this will be 0, that is body terminal should be connected with 0 potential like this, and the source terminal is also connected with 0 potential like this. But the drain terminal is applied with a small voltage of drain potential with respect to grounded, and that potential is very small. That means we are applying VDS very less than the required potential, which is I mentioned here less than 50 millivolt. So or equal to 50 millivolt, very less potential has been applied. In that condition, definitely, since we are applied a potential and we know that this potential is positive, and now just try to see that this is an N plus region and this is a P region, and if this is grounded, that means these two are connected together. In that case, we can see that there must exist a diode, between these two, that is this side is positive and this side is negative. So if we are having a diode and we know what is the behavior of the diode, when we reverse bias the diode. Why we are reverse biasing the diode? Because the diode P region, because for this diode the P region is connected with zero potential and N region is connected with positive potential, then definitely we are getting a reverse biasing of the diode. So we have enhanced our condition of equilibrium. Initially when it is in equilibrium, we definitely have a junction, and I have given you the analysis that how the junction is behaving. It will exert a force if the electrons will get entered. So now also if we have a junction here, then this junction will be created like this, the reverse biasing, and we can maintain a junction that will be contain so many ions like this. Here also we are having a junction, but the width of the junction is very less and it is not going to increase. Why? Here we are having 0 and 0. That means this particular PN junction is not applied with any particular potential. This is P, this is N. So we are also having a diode, but this diode is again in equilibrium. So always this diode will be in equilibrium, and this diode we are applying the reverse potential if we are increasing the potential at the drain terminal. So that means if the reverse biasing is increasing and the junction potential is increasing, definitely we are having more number of ions. Now what will happen if we are having more number of ions, and initially we know that we are having the ions here also, but after increasing the potential here, the electrons here, we don't have any electrons here, because the electrons will get experience the force, and these electrons will move in this direction. Which direction? These electrons will get moved in this direction, and because of application of this potential and the electron is moving in this direction, we definitely have a current. Where is the direction of current? We are having a current in this direction. What is the direction of current? The direction of current will be in this direction. So in the previous case, we don't have any current. Why we don't have any current? Because the drain potential will be equal to 0. Until unless we are applying a drain potential, we don't have a current. So definitely we are having a current here, and this is because of the electrons which is moved, and because of the present potentials, which is a positive zero potential here, a positive potential here. This electron is experience a force in this direction, and if it is goes inside this electric field, this is experience a force and it will get swept within the drain region or drain electrode. So we are having ions here, but here we are having the ions like this, or no electrons, and only we are having the ions that is present like this. Okay. So if you draw separately this particular region, then we come to know that what is the condition of this particular region. Now we can say that the electrons depth, the depth of electrons that is present, the concentration of electron that is present on source side, because this is the source side, and the concentration of electron that is present on the drain side are unequal. Why unequal? Because this potential will take the electrons out, and we are having only the ions that is present here. And now if you are talking about the equipotential surface, the equipotential surface, again we are having positive, that has to be satisfied with the negative charges on the semiconductor side, and that negative charges on the source side will be compensated by the electrons plus ions, but on the drain side they will be compensated by the ions only, because the electrons doesn't we don't have any electrons on the drain side, because the positive has been compensated by the negative ions. So in that case, we are having, if VDS is greater than 0, we definitely have, already we said that VGS is greater than threshold voltage, we definitely have the current that is non-equal to 0. And if we are having the current that is not equal to 0, then we can say that the magnitude of current is increased, will be increased by increasing the drain to source voltage. So I can see that the ID current is increasing if we increase the drain to source voltage. And in addition to this, we can say that the channel depth, the depth of the channel is more towards the source side, and the depth of the channel is decreasing towards the drain side. So just I am drawing this particular line, and I will show the depth of the channel. So initially when we have this, suppose this is the source side and this is the drain side, and this is the depth of the channel. When we apply the gate terminal voltage VGS is greater than threshold voltage, and we not apply any potential at the drain terminal, the voltage will be equal to 0. The depth of the channel will be equal on both sides. So I mean to say that suppose this is the depth of the channel on drain side, and suppose this is the depth of the channel on source side, they are equal. And in which condition? In this first condition. So I want to write here the depth of the channel. In this first condition, we want to write the depth of channel. Depth of channel is equal. Depth of the channel is equal at source and drain end, both ends. Okay. So I mean to say that here what is the potential of VDS? The VDS potential will be equal to 0. So as we increase the VDS potential, the depth of the channel at the source end will not going to change. Why the depth of the channel is not going to change? Because the source and the body terminal, we are not going to change the potential. They are always at 0 potential. But at the drain side, we are decreasing. As we are increasing the potential, the depth of the channel will going on decrease. So depth of the channel is decreasing. At this condition, we can say that here we have increased the potential, that is VDS is, suppose we are applying that is 40 millivolt like this. And if we increase more number of potential, then we can say that the depth of the channel will be decreased more and more. So the channel depth is decreasing in this direction. So this is the value of VDS, and this is going to be less as we increase the voltage more and more. So initially, if I want to visualize this one, the electrons initially when VDS is equal to 0, we are having equal number of electrons on source and drain side. As we are increasing the voltage here, the electrons will get removed from this side, and we are having more number of ions. We are having more and more number of ions on this side, on the other side. So we are having the ions. That means the density of electrons is going on reducing. If you are increasing the more potential, then we can say that we are having more number of ions and less number of electrons. But the source end, since it is connected always with 0 potential, there is no formation of more number of ions. Only the ions will get formed on the other side. That is, we are having more number of ions here. So as we are increasing the VDS value from 0 potential to a higher potential, we are having the depth of the channel is decreasing, and the shape of the channel, now this is called the channel. Now this is called the channel in which we are only having the electrons. Initially, whatever the ions that is present initially, due to the voltage that is applied at the gate terminal voltage, which is less than the threshold voltage, that ion should be present here. But as we increase the VDS value, we are having less number of electrons on the drain side, and the ions concentration is increasing. And now the capacitor is happy again. Why the capacitor is happy? Because we are having the equipotential surface. The positive has to be compensated with negative. Here the positive charge is compensated by the electrons. Here the positive charges are compensated by the ions, but they are getting compensated because the capacitor should be happy. So here we have the analysis. In that condition, I already said that your current is depending on VDS, and we are writing a final equation here. The ID current is equal to, we just write ID current is equal to, this is mu n COX and W upon L, which is multiplied by VGS minus VT, and this is multiplied by VDS minus VDS square upon 2. This will be the final equation that can be used in a condition when what is the condition? When we are applying VGS greater than the threshold voltage, and when we are applying VDS is very less, In that condition, we have the equation. And here we can see that ID is depending on VDS. But the value of VDS is very small. If VDS value is very small, value of VDS is very small. That is approximately 50 millivolt. If VDS is very small, we can ignore this particular terminology in this equation. This particular term in this equation, not terminology, only the term. In that condition, I can write, if you ignore this particular term, then I can write the ID current is equal to, we know what is mu n COX. Mu n COX is nothing but called the transconductance parameter. What is this called? This is called transconductance parameter.
and the unit of this transconductance parameter is, we just write here parameter, this is mu n Cux parameter, and if the unit of this transconductance parameter is ampere per voltage square, and W upon L here is known as aspect ratio. What is this called? This is called aspect ratio. We can have the aspect ratio in our TV mobiles everywhere. This VGS minus VT, what is this is called? This is known as overdrive voltage. What this is called? This is known as overdrive voltage. So I have everything with us. Now we want to write down what is the ID current equation if we apply a very less potential. So I mean to say that the equation of ID current here, the ID current equation is equal to how much? This is equal to mu n Cox, approximately equal to, because we have ignored VDS square divided by 2, VD mu n Cox W upon L, and we are having this is VGS minus VT, and so we are having multiplied with the VDS. And if someone asks you what will be the resistance, the output resistance. So if someone asks you what will be the output resistance here, so I mean to find out the output resistance. So output resistance is always found in between the output voltage which is given by VDS and the output current. So if you find out the small signal resistance, then I mean to say that for a small signal resistance, the resistance can be found out RD, that is the output resistance can be found out by change in the voltage divided by the change in current, or we can say 1 upon RD can be find out the small change in the current divided by the small change in the voltage value VDS. So we are having this is VDS, this is ID. So I just mean to find out what is RD or what is 1 upon RD. So if you find out what is 1 upon RD, then we have to differentiate this ID with respect to, take the derivative of this ID, change in the ID with respect to change in VDS. Then we can write this is given by mu n Cox W upon L. This is all constant and VGS is constant, threshold voltage is constant. Only the thing that is changing is VDS. If you differentiate with respect to VDS, then we are having the following formula. Then if someone asks you what is RD resistance, then I can say this will be given by 1 divided by mu n Cox W upon L, and this has to be multiplied by VGS minus VT. So this is the resistance. Now come to the question. In this question, with the potential difference between the source and the drain kept small, that is VDS is small, the MOSFET behaves as a resistance. Yes, we find out the MOSFET is behaving as a resistance whose value varies inversely with. So this is the things. So overdrive voltage which is given by VGS minus VT, which is inversely proportional to resistance, this is going to be tick mark. The aspect ratio, that is W upon L, which is also inversely proportional. The transconductance parameter which is equal to mu n Cox. I have already written here mu n Cox is the transconductance parameter which is also inversely proportional. His statement in the question is not suitable. This is wrong. So the correct answer for this MSQ is option A, B and C. So I will give you the another analysis which is channel length modulation. In addition to this particular fact that I have written here, what will happen if you increase the voltage above the 50 millivolt. So this part has to be analyzed in the next lecture. Till then, you just analyze your theory, your confidence in terms of this particular semiconductor devices, and we come to know that if you increase the VDS value, the width of the channel, that is depth of the channel, we are analyzing that it is less towards the drain side and more towards the source side, and that particular shape that we have in the channel is known as the tapered shape channel. So the shape of this particular channel is known as the tapered shape channel. So we have seen all those things clearly. So the shape of the channel that we have here is known as the tapered shape channel. So this is known as tapered shape channel. So channel is now tapered shape. So channel means the region in which we are having the electrons only, not the ions. So tapered channel, okay, we are having. So that means the electrons concentration is having a shape which is having a slope, okay. So this is the condition that we have analyzed. So in the next lecture, we are going to increase the VDS value more than 50 millivolt and going to analyze what is channel length modulation, what is how we have to consider the channel length modulation, what is the change we are expecting in the current equation when we increase the voltage VDS above the threshold voltage, when we increase the VDS above 50 millivolt, not threshold voltage. Okay. So the threshold voltage is the voltage that is applied at the gate terminal, but in the next class we are going to analyze about the drain terminal voltage, which is increasing above 50 millivolt. That means this condition. So be connected, be confident, and create your own story about this MOSFET by analyzing my theory, what I have said in this MOSTOK, and this is nothing but a crash course to give you a proper idea about the MOSFET and the behavior of the semiconductor. We have analyzed when we change the voltage, that is gate terminal voltage and drain terminal voltage, with one equation. Thank you.